Hello and welcome to the IDX webinar. I'd like to welcome you on behalf of Washington State University and the Civil Engineering Department at WSU specifically. Today what you're going to see is a webinar. This webinar is put on by students here at Washington State University in their capstone design class. And this webinar is intended to provide you with an understanding what their project is all about over the course of the year. We'd really appreciate any feedback you guys have along the way. And so as they present information and material to you guys, we'd really appreciate any comments or questions. And down on the website, if you're watching live, you'll be able to see that there's a place for putting in some of those questions down there. So please ask that you put those in and just specify what the different topic of those questions are. Again, we're really excited that you're able to join us today. I think the work that the students have done has been tremendous up until this point, and look forward to seeing what they have to present to you guys. So with that, as you can see here, there are several students from our Civil Engineering Department that are presenting this, again, for their capstone. And so with no further ado, we'll get them up here to present.
Hi, I'm Casey Torres, and we're the Integrated Design Experience, or as we're going to call it, IDX. We are performing a supply chain analysis for the conversion of biomass into aviation biofuel and bio-based co-products, a project in conjunction with NARA, the Northwest Advanced Renewables Alliance. NARA has 5 main goals. They're to develop a framework for a sustainable biojet fuel industry in the Pacific Northwest, to create products from lignin, which will be co-products, sustain and enhance rural economic development, facilitate and promote regional supply chain coalitions, and improve bioenergy literacy. The purpose of IDX is supply chain analysis, but we want to align our goals with NARA's as much as possible. Here's a graphical representation of our supply chain. We're going to be discussing each portion in teams of 2, but very simply stated, it begins with moving woody biomass to a pulp and paper mill where liquids depot will be located. Here it is treated and the biomass is separated into lignin and a sugar slurry. Lignin products can then move to the lignin market after recovery process, and the sugar slurry can go straight to a sugar market where it can be further refined into isobutanol and ultimately jet fuel. We're going to begin with the woody biomass. The team responsible for this portion consists of myself and Tyler Kirshner. Biomass is organic material from a plant or animal that is available on a renewable basis. We're concerned with woody biomass, specifically softwood forest residuals. This includes tree tops, limbs, stumps, essentially all the non-merchantable wood byproducts left after a commercial harvest or thinning operation. Now normally these residuals are put into piles, which are called slash piles, and then burned for wildfire mitigation. We however want to utilize this resource. Burning a slash is a waste. Environmentally, using residuals as feedstock for biofuels reduces carbon and greenhouse gas emissions by reducing the use of petroleum-based fuels. A social benefit to using biofuels is a step closer to energy independence, which requires diversified energy sources. Now, energy security, or at least less of a dependence on foreign oil, has strong social support. Economically, the low cost of crude oil right now most likely prevents biofuels from being cost competitive with fossil fuels. However, the price of oil is very unstable. We've especially seen this in the past 15 months. The price of oil will rebound, which will hopefully lead to a profitable biofuel industry. And we chose to focus on the aviation market for biofuel because it's a safe bet. PricewaterhouseCoopers and the FAA in separate reports have projected that air traffic will double over the next 20 years. We also know that planes are not easily electrified. So our supply chain analysis is on the Olympic Peninsula in western Washington. The Olympic Peninsula has an abundance of woody biomass and was also selected in part due to the willingness of stakeholders in the region to work with IDX. We're currently looking into 2 pulp and paper mills to co-locate a biofuels conversion facility, which is going to include a liquids depot and a lignin recovery facility. The 2 mills are the Port Townsend Paper Company in Jefferson County and the Nippon Paper Industries mill in Clallam County, which is in Port Angeles. The accessibility of both these mills is pretty good. Port Angeles is located along Highway 101, and Jefferson County is just a few miles north of it. They're both also relatively close to the SeaTac Airport, which is a huge jet fuel market. And now from one Olympic Peninsula native to another, here to discuss the availability of woody biomass on the peninsula and the costs associated with the collection, processing, and transportation of it to the mills is Tyler Kirshner.
Hello, I'm going to present you with the cost and supply data for our supply chain analysis. This was used to determine that it was both economically feasible and sustainable on the Olympic Peninsula. The first important factor in determining whether or not this would work was to make sure there was a sustainable supply of woody biomass available on the Olympic Peninsula. This was done using ArcGIS to use specified radiuses to have an area, and then using NARA TPO woody biomass density data to find volumes in bone-dry tons of woody biomass availability. An important thing to note is that the darker the green on these maps, the higher the woody biomass availability density in those locations. Our first location we looked at was Port Townsend Paper Corporation. As you can see, as the radius grew, the biomass available grew exponentially, with the 50-mile radius having 112,000 bone-dry tons of woody biomass available, whereas a 10-mile radius only has 6,000 bone-dry tons available. The second location we looked at was Nippon Paper Industries in Port Angeles, Washington. As you can see, there's a much higher density of woody biomass available in the 50-mile radius. In fact, it is double that of Port Townsend Paper at 224,000 bone-dry tons. This is largely due to the fact to its vicinity of western Calhoun County, which is far less populated and has a higher density of woody biomass available. Another important factor in determining whether or not this supply chain analysis would work is the cost. This was done using the USFS transportation costing model. This is a very good model, but not exact due to it being based on some assumptions. Those assumptions include an assumed solid volume factor, an assumed moisture content, and assuming that all wood species harvested would be Douglas fir. Along with that assumption, it is also only purely based on cost. It does not take into account profit, taxes, or anything else like that. As far as assumptions we made when running the model, we assumed a 10-mile gravel road to 20-mile two-lane paved to 20-mile state highway ratio for a 50-mile radius, and use that same ratio for the smaller radii. As you can see, the prices vary depending on what truck you use to transport the chips. As a 150 cubic yard truck is around $50 a bone-dry ton, which is shown in the picture at the top of the slide. Whereas on a 100 cubic yard truck, which is a typical roll-off truck, is over $60 a bone-dry ton. So it's more feasible to use the bigger trucks if they're available. Another important factor to note that we used was we decided to have the chipping done on site with the horizontal chipper at the landing, and then haul the chips already broken down in the trucks in order to have more density, therefore more material in each truck per trip, as opposed to chipping at the mill with electricity, which would reduce our carbon emissions, but it would not make it economically feasible due to the fact that there would not be near as much material per trip moved. Once the woody chips get to the mill gate, the next part of our process is the liquids depot, which Desiree will tell you about.
Hi, my name is Desiree Seiler, and I'm going to be talking about the liquids depot, which is the second step in the NARA process, along with my classmate Dane. This graphic shows a general overview of the processes that go on in the liquids depot. Once the wood chips go through these processes, they will be transformed into a fermentable sugar slurry and a lignin byproduct. The first step for these wood chips when they enter the liquids depot is to go into a digester, which is where the calcium bisulfite pretreatment occurs. Steam is also introduced into this chemical process, and any heat made is then recycled back into the depot as an energy source. Optimal digester parameters were found to be 145 degrees Celsius, a pressure of 315 kilopascals, a cook time ranging between 180 and 240 minutes, and a general water to feedstock ratio of 4:1. All of this data and numerous other experiments can be found on the NARA cumulative report, which really shows that these parameters are truly the most effective and efficient way to extract sugar from our woody biomass. Once the wood chips go through the digester, they're then in the form of a pretreatment liquor. The pretreatment liquor is then sent off to a blow and a flash tank, where both the temperature and pressure of the liquor is reduced. Again, any heat coming out of this process is recycled back into the depot as an energy source. Once the liquor goes through the blow and flash tank, it enters a washing station, which mainly flushes out any excess liquids and results in a spent sulfite liquor, which is sent off to the lignin recovery depot, and a sugar slurry, which will then go through an enzymatic hydrolysis, which Dane will now talk about.
Thanks, Destry. So I'm Dane Kamenzine, and I'll be covering the latter portion of the processes that occur in the liquid depot. The first of those that I'd like to talk about is enzymatic hydrolysis. Its main purpose is to convert cellulose and hemicellulose into fermentable sugars, such as glucose. It's a process that we should all be familiar with because it occurs in our stomachs every day. And in this situation, we're going to produce two streams, a liquid sugar slurry and a residual solid bunch that contains mostly insoluble lignin. And one of the big advantages of this is that it's conducted in relatively mild conditions. You can see in that picture on the left, it's the material that goes into enzymatic hydrolysis, and on the right, it's the sugar slurry that comes out of enzymatic hydrolysis. This diagram represents everything that comes into the enzymatic hydrolysis process. Water is added, lime is added to raise the pH, and then the enzymes can be added. We have three types of cellulase enzymes. Once the enzymes are added, we can raise the temperature to approximately 120 degrees Fahrenheit or 50 degrees Celsius. And on an industrial scale, the process will take about 72 hours. So this graph represents everything that comes into the liquid depot. The yellow portion here is the insoluble liquid or lignin that is included in the residual solids from enzymatic hydrolysis. The orange portion up the top is the lignin that is dissolved in the acid from pretreatment. This hashed section down at the bottom is sugars that cannot be fermented. It's either because they're still in a cellulose because they weren't hydrolyzed or because they were dissolved during pretreatment. And this purple portion is mostly glucose, but it has some hemicellulosic sugars. And to speak more on that, I'm going to introduce Taylor Arndt and the sugar market.
Hi, my name is Taylor, and I'm joined here with Victor, and we're going to be talking to you today about the market for our sugar slurry as the sugar is produced out of the liquid depot. When doing our sugar market analysis, we looked specifically at other potential markets other than the aviation industry because we know that there's a potential market for our biofuel that way. But we wanted to make sure that in case that supply chain would have changed, we could look and make sure that our sugar could be sold elsewhere. But before we do that, we want to make sure that we understand what our sugar slurry consists of and how it relates to sugar that you may be familiar with. So what's in our sugar slurry? So our sugar slurry generally consists of cellulose, which is dominantly glucose. It also consists of other hemicellulosic material, which you see here of those monosaccharides. And this relates to common sugar that you may be familiar with, honey, high fructose corn syrup, and a regular table sugar. And these consist of sucrose, glucose, and fructose made up in mixtures and different compounds. So why this matters is that when we're looking at potential buyers of our sugar, we want to make sure that we're targeting those buyers that are interested in our specific sugar makeup. So when looking at our market for our sugar slurry, we have the dotted box here, which outlines our main facility mill. And we saw two potential situations. One would be sugar would be our main out-of-mill product, which you see down here. And then fermentation, another scenario would be fermentation would occur inside the mill, and the isobutanol would be our main out-of-mill product. Now, based on full-scale operation on the peninsula, we could, with a rough estimate, we could produce about 10,000 bone-dried tons per year of glucose. In the same input, in the same scale market on the peninsula, we could produce about 15 million gallons a year of isobutanol. So all in all, this shows the different market options available for these two market scenarios for our sugar slurry. And next I'm going to pass it off to Victor, and he's going to go more in depth into these different scenarios.
Thank you, Taylor. Yeah, so as he said, we were mainly analyzing two different scenarios for our sugar. The first scenario, as he said, is sugar as our main out-of-mill product, as you can see here. And we're going to quickly look through three different potential markets for our sugar. The first of these is the use of sugar for the creation of butanidol, otherwise known as BDO. And this is a chemical that's used in the production of many different products, plastics, other synthetic materials. The second one that we have over here is the livestock feed industry. And currently, sugar slurry isn't established in this market, but a very similar product called wood molasses is. And the wood molasses and the sugar slurry both contain the cellulosic and hemicellulosic sugars. The third market that we're looking at as a potential for our sugar as a product is with companies that produce isobutanol. They take this sugar and they ferment it to produce this alcohol. One company that does this is Gevo, who is actually an industry partner with the NARA project. And next we have our second scenario that we looked at, which is the situation in which our sugar is fermented into isobutanol inside of our mill. And if this were the situation, the petrochemical industry is a huge potential market for the sale of isobutanol. This is because petrochemical companies can use isobutanol as a substitute for petroleum in the manufacture of their products. Many chemical companies have already invested in bio-based alternatives for their products. Companies like Dow Chemical, BASF, and DuPont, which are shown here on the screen. Also, the petrochemical industry has been experiencing growth in the last several years and is projected to continue to grow in the years to come. As you can see here, the numbers, not only for revenue, but also just the number of companies are expected to grow. This growth in the petrochemical industry represents a growth in the potential market for isobutanol as a product. However, isobutanol and sugar are not the only potential products that could come from our NARA process, and to discuss another potential product, I'll introduce Brent.
Thank you, Victor. As Victor said, my name is Brent, and I will be presenting the lignin recovery systems along with my partner Cody. Now, as Casey stated in the beginning, NARA's only goal is not to produce isobutanol, but also co-products of lignin. What is lignin? Lignin is basically the glue that holds the tree together. By percentage, lignin nearly makes up the same composition as cellulose. Lignin is also the second most abundant polymer in the world. Also, in this picture, as we can see right here, there is dried up lignin in a powder form, which is what we'll be seeking in our end process after recovery. But how do we get there? So as we can see in our plant, we're being fed two different types of liquors in our diagram. First off, we have the craft liquor, which is currently just being burned off in pulp mills as hog fuel. Then we have our SSL, which is our spent sulfite liquor. Both will go through a filtration and then into our lignin recovery system. In the end, we will end with craft lignin and lignosulfides in the powdered form that was depicted in the picture before. It should also be known that each goes through, the SSL and craft liquor go through two separate filtration systems, as the SSL could contain sulfides and cannot be mixed, but they go through one lignin recovery system. Also, there have been multiple pilot systems where a lignin recovery system has been placed into a mill and has worked. Now, to go in more about the process and how we're actually going to recover the lignin, I will hand it over to Cody.
Thanks, Brent. So looking at the incoming streams of lignin into our lignin recovery facility, there's a key characteristic that differentiates the two liquors. Spent sulfite liquor is water soluble, whereas craft liquor is acid soluble. What this means is that to get lignin out of spent sulfite liquor, we need to precipitate it with calcium hydroxide. This solution is then pushed through a semi-permeable membrane where the lignin is separated from the rest of the slurry. This process is called ultrafiltration, and more specifically, the Howard process, and is used in sulfite mills around the world. In contrast, the craft lignin recovery from craft liquor is a very heavily researched field right now because craft liquor is primarily used to fire the boilers in the mill, as Brent previously mentioned. But there are several companies that have developed and implemented systems for the recovery of craft lignin from the liquor, and I have provided a simplified flowchart of their process. First, an acid is added to this solution, usually carbon dioxide. It is then precipitated
coagulated, filtered, dried, and ground into a dried powder. This powder can then be bagged and transported on trucks to its final destination. And out of our system comes two separate forms of lignin, the lignosulfonates and the craft lignin. And here to talk a little bit more about what we can do with these lignins is Joe Emily.
Thank you, Cody. I'm Joe Malloy, and I work with Tyler Thornton. We analyze a lignin market and the potentials of that industry. I'd like to start off first with this figure. It shows a volume at the bottom versus two values. On the close side, we have the actual value of the lignin in the market, and on the far side of me is the potential market value of end products. I know it's a little confusing, so I'm going to break it down. On the bottom here, I highlighted two boxes. We have low purity lignin going over to energy. The horizontal line represents a very limited added value for that end product, as opposed to something like craft lignin being transferred into activated carbon or carbon fibers. As you can see, there's a very vertical sloping arrow, and that shows that there's a much more added value to change it into those products. And also take note that the activated carbon and carbon fibers, they have more value than energy. So it would seem that it would be more of a better investment to change it over to activated carbon or carbon fibers. So just a quick overview of the supply of lignin. The potential world production of biomass is 200 billion tons. And from that, we create 50 million tons a year. But the interesting fact is that only 2% is actually converted into products. This leaves a lot of potential for products such as the ones listed on the column closest to me. Things like aromatic compounds, resins, activated carbons, as I stated before, and sealants, among others that are there. And on the far side, we have, I wanted to put up there again the 6 different types of lignin. And I highlighted the 3 at the bottom because they're the 3 that are currently the most abundant in the market. So I just wanted to put an incentive out there for the reason for switching over to lignin, or using lignin more accurately as a green alternative. It reduces your carbon footprint. You can use it as a fuel, and you're diversifying your markets. For example, like we did if you do what we were talking about by installing depots to recover lignin, you can have 2 revenue streams, one from your typical mill processes, as well as selling off that lignin to potential buyers that want to turn that into end products. And to talk more about the lignin market, I'll turn it over to Tyler Thornton.
All right, that is Tyler Thornton, as Joey just mentioned, and as he explained so well, and we heard that word potential so many times as he discussed different uses for lignin, and I think it's very critical to point out that it's not just potential, it's not just a pie in the sky kind of scenario. There's actually industry leaders and proactive governments around the world that are investing real dollars in this within the last few years. From Finland to South Africa, from France to Brazil, we have massive amounts of money, as you can see right here, being poured into both lignin research and actual physical lignin producing plants. Bringing things a little bit closer to home here in North America, we see Beauregard showing up in a big way again, joint venturing this time with Rainier down in Florida. West Fraser, as well as the Domtar Corporation, continue to invest heavily in the Canadian market. Interestingly enough, Domtar actually, during a rectification of one of their existing facilities in North Carolina, they actually added a significant amount of their money into adding a revenue-adding product such as lignin into their production facility. What do we notice about these companies and these investments over here in North America? We see Quebec, we see Canada, we see Florida, we see North Carolina. All these are in the eastern side of the United States and in North America in general. This really, I believe, is indicative of an enormous potential here in the Northwest market. We have every bit as much biomass and an incredible rich history in forest products already. And I think we're ready to take a next step into adding another product on the market. There's so many different potential markets that we have here in the Northwest, but one we just decided to highlight a little bit more this time that we're meeting together is building materials. Things like plywood, particle board, oriented strand board, and even gypsum board. Now, what would lignin be used for in these products? Well, just actually how nature has intended lignin to be used as a binder, as an adhesive to hold these products together. Just looking at this GIS map that we have here of the peninsula area, hopefully you can see there that there's both plenty of veneer plywood as well as engineered wood product mills in this general area, all conveniently collected together by railroads. But if we expand our search a little bit wider into the four-state area, we can quickly see that there's an incredible amount, particularly down the Oregon coast there, of more mills producing these materials, as well as two more potential market uses, such as fuel pellets and then there is the particle board showing up again. As we all know very, very well here, the housing market really has struggled in the past few years, but many market investigators have really showed a trend in the future of up, all going up there. But looking at plywood itself, coming particularly from India and China, imports of these imports have only increased in the last few years to meet this upcoming demand. As a domestic supplier, particularly here in the Northwest, as you saw on those maps, we have so many mills producing these materials. If we can make a safer by replacing things like formaldehyde with lignin and make things cheaper and greener in the overall scheme of things, I believe that we can really compete more in this market. In conclusion, as far as the lignin side of things, as you've no doubt seen, there's really tremendous future growth in so many different ways that you could use lignin. It adds really a key component, a key revenue stream. Rather than wasting a co-product in these biorefining processes, use that as a revenue stream using already your existing material. Global investment, you've seen from my slides there that both governments and private industry have been heavily investing in this product right now as we speak. We have an opportunity here in the Northwest, we really do, to gain a strategic foothold, if you will, in this really this expanding market in the future. That actually brings us to the end of our presentation here today. I really appreciate you all for tuning in, and we actually hope that you'll be joining us October 28th. We'll be diving a little bit more into site-specific inventories in regards to these projects. As far as I've heard, there have not been any questions submitted via our web format right now, but if there are any questions or comments, please do submit them via email and we'll get back to them as soon as possible. Thank you so much again.